Okay, so page 5 in your packet. We'll do number 6. We'll do a curve sketch problem here. We need separate sheets to work out the problems. We can do that. I have some scratch sheet up here too. Okay, so curve sketching. We're going to find go through first derivative test, find relative max, relative min, increase, decrease, and then we'll do the second derivative test for concavity, points of inflection, concave up, concave down, identify order pairs, sketch the graph, and then find sketch the graph and find absolute max, absolute min as well. Okay, so f prime first. Okay, so power rule for 1/2 x. 1/2. Cosine becomes negative sine. So there's our derivative. Okay. And to find critical points, we set our derivative equal to 0, right? Okay. Sine x equals negative 1/2. Right, so thinking about where sine is equal to negative 1/2, think about our unit circle values. We know sine is negative in the third and fourth quadrant. So that's going to be in that pi over 6 family. So 7 pi over 6, 11 pi over 6, right? The problem is that these values are not inside the interval. Right? So if you think about a number line here, if I stretch from negative pi to pi, 7 pi over 6 is more than pi, so that's a little bit outside my interval. And so is 11 pi over 6, right? It's further to the greater than 1 pi because that fraction is larger than 1. So what can we do to find coterminal angles that are potentially in this region? Subtract 2 pi, yeah. So if I want to subtract 2 pi just to match the common denominator, I'll subtract 12 pi over 6. So we're finding variations of our solution. So subtract 12 pi over 6, 7 minus 12 is negative 5. And 11 minus 12 is negative 1. Okay, so this is better because negative pi over 6 is going to be slightly to the left of 0. Negative 5 pi over 6 is less than negative 1. So we know both of these are safe. They're both going to be inside our interval. So we can create our slope sine line now. We have our endpoints from negative pi to pi. Okay, we're going to test our find some test points. And then test points will go against our derivative function, right? Or plug into our derivative function. So unfortunately, there's not going to be an easy value for us to find between negative pi and negative pi power 6. They're really close to each other. But we know that if I can find some behavior, I know that they're going to alternate. Okay? So between negative pi over 6 and pi, that's easy. I can choose 0, right? Anytime I can take advantage of 0. Between negative 1 pi over 6 and negative 5 pi over 6, I'll choose negative 2 pi over 6. How's that? Or better yet, negative 3 pi over 6. Because that's negative pi over 2, and it's easier to plug something in terms of negative pi over 2. Okay, so let's test 0 first. 0 in for x, sine of 0 is going to be 0. 0 plus 1/2 is 1/2, so that's positive. So I know my graph is going to be rising in that interval. Negative pi over 2. If we don't recognize negative pi over 2, we can always do what to make it more familiar? Hmm? No, if something is not in that interval from 0 to 2 pi, what can we do? Add 2 pi, right? Or add or subtract 2 pi to get it to. So if I do negative pi over 2 plus 4 pi over 2, that's 3 pi over 2. And 3 pi over 2, we recognize, right? Sine 3 pi over 2 is negative 1. Negative 1 plus 1/2 is negative. So we can't find anything here, but it's going to be alternating. So Jack, we're on the review packet from yesterday that you picked up yesterday on page 5. It's a help session packet. Oh. Yeah. Page 5. Okay, so we can expect a few things, right? We know that there is a relative maximum at negative 5 pi over 6, and there's a relative minimum at negative pi over 6. Yeah, some pages that didn't provide any work.
I think you gave me the key.
Yeah, I did, because I didn't have some of the pages are just keys. So if you just use on a separate sheet to work.
You're on page 6 of the.
Is your say test review packet? Yeah, that's it. That's it. Yeah, I got it. So I didn't create a blank copy. I just had the key.
Blank on the other packet on page 6.
Oh, it is. Oh, okay, okay, yeah. So you have space to work below. Okay. Okay, so we know where our relative max, we know where our relative mins are. Okay, so we're gonna move on to F double prime. So we can gather information about concavity. So let's go ahead and find our second derivative function. Okay, so second derivative, 1/2 goes to 0, sine x becomes cosine x. Okay, set our second derivative equal to 0. So again, same interval here from negative pi to pi. Okay, so where's cosine equal to 0? Initially.
Pi over 2 and 3 pi over 2.
Yeah, pi over 2, 3 pi over 2. Now, if you think about these critical points, it's one is inside the interval, but the other is not, right? So from negative pi to pi, pi over 2 is safe, but 3 pi over 2 is outside of our interval. So what can we do to 3 pi over 2 to find another variation of it to see if it will land inside the interval? Subtract 2 pi. Okay, so we have pi over 2 and negative pi over 2, and those are what we want, safely both inside our interval. Okay, so this is my second derivative sign line here. I'm going to choose values in each subinterval to test against my second derivative function. So anytime I can involve 0, it's going to be easy for me. Between pi over 2 and pi, I can choose 2 pi over 3. All right, so any of the second quadrants will work. Between negative pi over 2 and negative pi over 2, I'll choose negative 2 pi over 3. Okay, let's start with 0. It's easiest here. So cosine of 0 is what? So it's positive. So that means is what? What does that mean? Second derivative positive means
Concave up.
concave up. 2 pi over 3, cosine 2 pi over 3, is that positive or negative? Negative, right? Cosine in the second quadrant is negative. Now, just to double check here, we are probably expecting it to alternate, but just for practice purposes, if we don't recognize negative 2 pi over 3, what can we do to make it more familiar? Add 2 pi. So if I add 4 pi, sorry, if I add 6 pi over 3, I get 4 pi over 3 and still negative third quadrant. Okay. Cosine of 4 pi over 3 is in the third quadrant. So based off of these signs here, what can we conclude?
Negative 1/2 and pi over 2 are the POIs.
Yeah, so negative pi over 2 and pi over 2, right? Good, we have 2 points of inflections. Okay, we're ready to sketch our graph. Okay, our intervals from negative pi to pi. So we're going to try to find, at least our endpoints so that we can figure out where we're going to begin and end, and then we can follow the path of our graph and then sketch the graph that way, and then we can work in the curves, right? Okay, so let's find our endpoints so we can kind of have an idea where to start. F of negative pi. So anytime I'm looking for physical locations, I'm going to be inserting these x values into the original function, right? So I get negative pi times 1/2, which is negative pi over 2, minus cosine of negative pi. If you don't recognize negative pi, you can add 2 pi to this. So cosine of pi is what? Goes to negative one. Negative one times negative one is positive one. Okay, so let's do a decimal approximation, right? So anytime you see pi, what's the easy number for us to replace that with?
3.
3, right? So this is negative 1.5 plus 1. So negative 0.5. Okay, so we can. Okay, let's see where we want to end up here. F of pi. So I have pi over 2 minus, same thing, negative 1. So I get, oh, this time it's pi over 2 plus 1. So it's 1.5 plus 1. So we end up at 2.5. Okay, so my graph will start at negative 0.5 and it's going to end up at 1.5.
I have a question. Why would you choose to replace pi with 3?
Just so we can have an easier time plotting the points.
Okay. But do you have to be with 3 or pi replace it with any number?
Well, what's pi equal to?
Wasn't that 2.6 around there?
I think that's 2.71 is E, right? So pi is 3.14. So I just chose the closest whole number. So it's close enough to 3. Okay. Okay, so let's go ahead and start our sketch of our graph. We know we're going to start off at negative 0.5 and end up at 2.5. So I'll start off marking off negative pi. And I'll end up at pi. Okay, so based off of our slope sign line here, we want the graph to be rising to some relative max at negative 5 pi over 6, decreasing to some negative pi over 6, and it's going to continue rising all the way up to pi. So that should be closer to the left side. Okay, so we know it's going to be decreasing to some y value at negative pi over 6. Increasing first to negative 5 pi over 6. Decreasing to some y value at negative pi over 6. And it's going to increase the rest of the way up to pi, up to whatever we found this point is 2.5. So we don't know the curvature, but we know that's the path of the graph, right? There's a relative max, there's a relative min, and it's going to end up. Right. Okay, so we also know along this way where we can plot in where we think our points of inflections are. So points of inflection will be at negative pi over 2 and pi over 2. So I know negative pi over 2 is somewhere here. Right, between negative 5 pi over 6 and negative pi over 6. So I'll just highlight where I think that point is, right? We don't have to be super accurate. And then we also know that at pi over 2, there's a point of inflection. So pi over 2 is somewhere between 0 and pi. Okay, so now we can just sketch the graph based off of what we know to be true, right? Concave down first. Switches over to concave up. And then switches back to concave down. Okay, makes sense? Okay. So if I ask you all these statements about relative max, relative min, POI, it's easy, right? You can just pull all that from the sign line. But if I ask you for absolute max and absolute min, you know our absolute max is going to be this y value, right? And then where do you think our absolute min is going to be?
-0.5.
Or negative power 6. Or, right, we don't know where that value is specifically, but we know it's going to be at this point, right? So how can I find a specific y value?
If you draw it like in a way, can't that absolute min might be negative 0.5?
Yes, that's right. It could be. It could be. You're right. So what we can do is we can plot these points. Because this could be higher as well, right? We can plot these points back to the original function and just compare, right?
Yeah, that's what I did.
That's what I did. Okay. Okay. So yeah. So you're right. If your sketch of the graph is different, and that's with good reason, we can plug both of our relative max, relative min back into the original function and just compare, right? And whatever highest, we know, kind of have an idea where our absolute max, absolute min is. Okay. So okay. So we know. Let's go ahead and find those order pairs then, to our best of our ability. Negative 5/6. Okay, so back into the original function. Okay, so this is a little bit hard here, but let's see. I have negative 5 times 3, so negative 15 over 12. And then cosine negative 5/6. If you don't recognize that, add 2 pi to it. That's the same thing as cosine of 7/6. And that's the same thing as root 3 over 2.
15 right there.
I did 5 times 3.
Oh, okay.
Yeah, every time I see pi, I'm just going to think in terms of like, okay. So this is like negative 1.1 minus 0.7. So that's like around like negative 2-ish. So that's definitely, sorry. Oh, sorry, this is a minus a negative here, so plus. So negative 1.1 plus 0.7, so that's like, okay, so that's actually a little bit lower, but we know it's not going to be very high. So this is not going to be an absolute max, absolute min. It's just maybe it's a little bit lower than here, but we know it's going to be just a little bit higher than our starting point. Okay, but we're expecting this maybe to be an absolute minimum. Let's see what happens if I do f of negative 5/6 back into the original function. So this is negative 3 over 12, which is like negative 1/4, negative 0.25. And then cosine of negative 5/6, cosine is positive in the fourth quadrant. That's the same thing as 11/6. It'll be root 3 over 2. So that's like negative 0.5 minus 0.7. So that's like negative 1. So we know that it's going to be an absolute minimum. Yeah. Okay, so absolute minimum is around negative 1, and absolute maximum, we know it's going to be at this point here, so at 2.5. So we're just dealing with approximation here, not going to be not going to be really picky about you finding that exact value, but as long as you're trying. Yeah.
When you write down the points of inflection, the concave up stuff, do you need to include the y value
No.
too? Okay, so just the x.
Yeah, just the x, because I mean we could, but the thing is we kind of know where it's going to land. It kind of lands along the path of the graph, so it's not as important. But I would say that the endpoints and the relative max, relative min, those are more key.
Okay.
Okay. So back into your packet here, I want to do a particle motion problem with you. So this is page 7. I have the key here, but the problem is here, so we can just work it off on a separate sheet of paper. Okay. This is on the help session packet. Billy Grace, do you have that from yesterday? Yeah, I'm picking out from that packet. Okay, so particle motion, page 7 here. Okay, so it says find velocity, find where the particle is at rest, and find interval moving left and right. So this is particle motion build off of our velocity function. So here's our position function. We want to find the velocity function. We can find the derivative. Okay, what's the rule for e to the u?
E to the U times U.
E to the u times u prime. So our velocity function is just e to the cosecant of t times u prime. So u prime is the derivative of cosecant. Hello. Okay. What's cosecant's derivative? Yeah. Which is times 1, right? So yeah. Okay, so we set our velocity equal to 0. Which part do we not have to worry about? The e, because the e is just going to look like this, right? It's just an exponential function. That exponential function is always going to be living above the x-axis. So we know no solution will come from that. We can ignore that part. It's just this part we have to worry about. Okay. Now, I have an easier time thinking in terms of sine and cosine instead of cosecant, cotangent. So I'm going to rewrite this in terms of sine and cosine here. Okay, so cosecant is 1 over sine. Cotangent is cosine over sine. So it's really negative cosecant, sorry, cosine of t. Over sine squared of t. Okay. I want to figure out where the slope of velocity is 0. So the only place I care about where velocity is 0 is looking where? Numerator, yeah. Okay. There's a negative there, but if I just divide that negative over, it goes away. Okay, so where's cosine equal to 0? But our interval is only from pi over 6 to 5 pi over 6, so the only one we're going to keep is what? just pi over 2. Okay, so here's my velocity function. Sine line. Okay, so I can choose values in each subinterval. Okay, to plug in here. So between pi over 6 and pi over 2. Well, first off, we know our velocity is going to be 0 at pi over 2. Okay, so that's part B. Find particles at rest. So part B, we can say particles at rest when t is equal to pi over 2 because velocity is equal to 0. Part C says find interval where particles moving left and moving right. So we need to test these intervals here between pi over 6 and pi over 2. I'll choose pi over 4, or better yet, pi over 3. That's maybe easier. And then between pi over 2 and 5 pi over 6, that's the second quadrant, right? So I'll choose 2 pi over 3. Okay. Technically, I should be plugging it into the original velocity functions, but I know that this E is just going to be positive, nothing there. And I rearranged this to be this. So I'm just going to plug into this. But what's nice about the denominator? It's always what? Always positive. So we just ignore the denominator. So really, whatever we get from the numerator is going to be the sine of our velocity function. So pi over 3 in for cosine. Cosine of pi over 3 is positive or negative? Positive with a negative in front, so negative. Okay, cosine of 2 pi over 3. Second quadrant, cosine is negative with a negative, so it's positive. So we know our particle is moving to the left in this interval because velocity is less than 0, moving to the right in this interval because velocity is greater than 0, right? And we don't include the test points anymore, right? Test points is just to get the signs, but after that, our interval is just with our critical points. Okay, so if you see something like this on the test, this is a good example of a particle motion problem. Okay, questions? Okay, I'll stop there. But if you have any specific questions, I can help with that. And we're just going to continue hitting more types of problems Monday and Tuesday, as well as in class.